Okay, so here is the plan. So today we're just going to talk a little bit about chapter 8, and then tomorrow I'm going to kind of like go over chapters 1 through 6. Thursday you are going to give presentations and give me the project, like a little write-up of your answers for your project. Then on Tuesday at 7:30. We meet in this room for an exam. It will be, so it's 2 hours, it's a 2-part exam. Part 1 will be a test on chapter 8, and it'll be very much like the previous tests that we've had for the section. It's going to be just kind of 4 questions. And then the second part is going to be a comprehensive test, and it's going to be kind of more short answers, kind of multiple choice, small questions to do. Okay. Any questions about any of that? Okay, and so that will get us through then. So I know that Joe and Elijah, you're working on your project, your meeting today. I think you'll know what you have to do. You guys work with Eric, and you're okay. What about you guys? Have you been working on your project? And okay, did you have any questions for me or? No. Okay, so this afternoon and tomorrow afternoon, I'm available, to discuss if you want to do it. So. It's nice if you send me an email warning that especially if we're going to set up a meeting to do it. Okay, so chapter 8 was really just kind of like a sampling a little bit of multivariable calculus. So it basically what we did in chapters 1 through 6, which when we just looked at single variable functions, you can do that for multivariable functions. And we just did a sort of like a starter where we just showed that we can take derivatives and we can find maximums. And the way that we take derivatives is basically exactly the same as when we take derivatives in the one variable case. And the way we find maximums is also exactly the same. The only complication is that there's two things, there's going to have 2 equations to set equal to 0 rather than 1. And the second derivative test becomes a little bit more complicated. But that's basically it. So basically, however you treated one variable case is how you treat the 2 variable case. And again, so the overriding philosophy is that you treat the 2 variable case like the 1 variable case, and you can do that by keeping one variable constant and letting the other one vary. Okay? So when you keep one constant and you vary the other one, when you take the derivative with respect to the one that's varying, this thing will go away if you differentiate it. Okay. So here in this example I showed before, so here we have a problem of clearing a airport of fog, and there's 2 inputs. There's how much calories you have to put into the atmosphere to clear the fog, and then there's the temperature of the fog, right? So we're trying to figure out how much energy we need to clear the fog. So it depends on the temperature and how wet the fog is, how thick the fog is. And we see when we do this, right, we see a graph like this is where what we have done. This is not a contour map. What we've done here, this is like a cross section. So what we've done here is we've kept one variable fixed and treated it then as a function of just the temperature. And when we see this as a function of temperature, we see that this is a decreasing function. It's a decreasing of function because the thing's going down. As a function of wetness, it's an increasing function, right? Because as W increases, the values increase. So that's kind of what I meant by treating one variable constant and just allowing varying the other one. And so functions can be given to you either as a formula, and if it's a formula, then you'll have to take the partial derivatives of these guys. If it's a graph, it'll be either in two ways. It'll either be in a graph like this, where we have cross sections, or in a contour map, which I'll show you in a little bit, or in a table. So here is just a table. And so treating one variable as a constant while varying the other means that you only look at a row, a single row, or a single column. And so when we see this, we see that as this variable, in just the variable y, what happens as y increases? Well, we see that our function decreases. So this is a decreasing function of y. What happens when we go x? Well, that means we go down like this. We see that it's an increasing. So this is an increasing function of x and a decreasing function of y. And again, a basic tenet to which we've looked at all semester is the fact that we can use, if we know how something is changing, then we can predict values nearby. So for example, here, if I told you at some base point where we're at 0, 0, that the value of the function is 50, and that it goes, z goes up 3 units for every unit increase in x, and it goes down by 2 for every unit increase in y, what is going to be f 25? Well, we can approximate that by going to a base point. We add in what is going to be the change in x. And we were told that it goes up by 3. And it goes down by 2 by every change in y. Right? The change in x is 2. The change in y is 5. So this is going to be 50 plus 6 minus 10. I'm going to get 46. That's the answer. Okay. So, because what does this thing mean? Now we're getting at the idea of the partial derivative. So the partial derivative is the rate of change in that direction. So you just imagine yourself on a landscape. You've got an x direction and you've got a y direction. In the x direction, the partial derivative is the slope in that direction. So that could be increasing in that direction. So it's increasing by 3. The slope is 3 in that direction. In the y direction, it's going down by 2. So that's all it is. So just think of yourself in this abstract landscape. And so the other thing that you'll be given will be contour maps. And so the whole idea of a contour map is, again, we're just looking, just imagine us looking at some sort of landscape. Here, we've got X and Y. It's kind of like latitude and longitude, really. So given an X, Y, you know where you are in space. Okay, and the contour gives you the elevation, the height of the function. And so here we can see that there's a little hill here, right? Because it goes 5, 6, 7. So we should be able to imagine that as like a little hill that we go up here. Again, there's a little hill up here, right? 5, 6, 7, 8. There's a little hill there. And down here, we can kind of imagine that there's some kind of valley sort of going down there, right? So it's going towards here, and this valley is going off towards the northeast. So some people are really good at this. They can look at that and they can just imagine the landscape. That's just a skill. Some artists have it, but still, even if you can't see the thing, you should still be able to say, okay, maximum, 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 sort of going down there. And so how do we go about finding these contours? So here is a very straightforward function. Got R equals 350x plus 200y. Let's say we want to go about creating a contour map. How we do that? Well, what we do is we actually write down the contours. So like when R equals 4,000, you see that's just a normal XY equation, right? We know it's a straight line. So what we just do is we solve this for y. So this is going to be y. We're going to get to, well, we need to divide by 200. Divide by 200, that's 20. That's 1 3/4. And so it's going to be 20 minus 1 3/4 x. Okay, so 20 is going to be the y-intercept. 20 here, and it's going to go down by minus 1 3/4, and so we're going to have so this is going to be some value, I can't, whatever 20 divided by 1 3/4 is. We're just going to have a straight line joining those two, and that gives us a contour, and that gives us the 4,000 contour. Then we replace 4,000 by 8,000. And if we do that, we replace the 20 by the 40. And so we go up here to 40. It's going to have the same slope, so it's going to be parallel. And we're going to get a contour like that. The next one is going to be at 60. Again, it's going to be parallel. And then finally, we're going to have one at 80. Going to be parallel. This is 4,000, 8,000, 12,000, 16,000. And we've made ourselves a little contour map. And so if we say we're here, right, if we go in this direction or this direction, we're getting the same revenue. If we go in this direction, that's where revenue is increasing the fastest. Okay? So perpendicular to the contour is where it goes, increases the most. Along the contour, it's not changing at all. Okay, so that's what it looked like. And so after a while, you can look at these graphs, and you can kind of sort of figure out what's happening. So what's happening here? Can anyone see what's happening? So what's happening here when we go in this direction?
Looks like a hole.
Yeah, so it's going up here. It's going up here, up here, up here. So you definitely have a hole, but it's not a perfect hole, right? Because this is the only time that contours can cross is when they're the same contour. Right? Different contours can't cross. But so here is all the same level here. So it's like there's 4 hills and there's like kind of like thingies that way. And so maybe a mountain pass might be the best description for it. Okay, do I want to do that one? This one is exactly the same as that one. So we already kind of did this example. So. Okay, so remember there are 2 kinds of graphs. There are contour graphs, right? A contour graph is where you're on the XY plane and the contours show you the function output. The second type of graph you can have are cross sections. So cross sections are one where the horizontal axis is one of the input variables and the vertical axis is the output variable. So it's called a cross section, right? Because if we think we have a contour landscape here, the contour map sort of gives us a view from here, from up top. A cross section is now what it sounds like. It's actually we're making a cross through the landscape, and we're looking at it edge on to see it here. Okay, so which one of these can show a cross section of that function? Okay, so a cross section will look like some C. Oh no, we're fixing one of the variables with y held fixed. So it's going to be z equals 50 minus x squared plus 5c. So we've fixed y as some kind of constant. So this is going to be z equals some bigger constant. So where we put 50 and the 5c together minus x squared. So this is what cross sections look like. What is this? This is upside down parabolas, right? Okay, so which one of these are possible candidates? Which one of those are the upside down parabolas? B, C, and F, right? So they're the only possible ones, but it can't be C, right? Because it's just a simple number minus x squared. Right, so that means this thing here is going to have its maximum at x equals 0. So it's actually only B and F are possible cross sections. So all we're doing with these guys is we're just kind of like, the main thing we're doing is looking at their partial derivatives. Okay, and so the same thing is true for partial derivatives as it is for derivatives. The most important thing about a derivative is its sign. Is it positive? Is it negative? Is it 0? If it's positive, that means it's increasing in that direction. If it's negative, it means it's decreasing in that direction. If it's 0, it kind of means you're on the contour. It's not changing. So here we had this situation where we're looking at calories burned per minute as a function of a person's weight and speed. So This is the partial derivative with respect to W. Is it positive or negative? Well, let's have a look. As W increases, what's happening to the number of calories burned? Is that increasing or decreasing? Increasing. So therefore, it's positive. What about as speed increases? Is the thing increasing or decreasing? It's increasing, right? So it's also positive. So what does that mean? Well, it means that the heavier a person is, the more calories they burn, the faster they go, the more calories they burn. So that's just putting it into words. We can estimate. And we do the estimation the same way that we do any estimation, right? We try to use small intervals and we try to put the thing in the middle. And so what is FW 160, 10 approximately equal to? Well, we're going to let W in, so 160, 10 is here. And we're going to let W vary, so we're going in this direction. So it's 10.2 minus 8.3 over 180 minus 140. And don't forget units. Units are going to be calories per minute per pound. Okay, because this is how much calories you're burning per increase in weight. Whereas the partial derivative in the other direction is the horizontal one. So it's going to be this one here. So that's going to be 10.8 minus 7.7 over 11 minus 9. And that's going to be calories per minute per mile per hour. And these numbers mean exactly what those units mean, right? This is how much increased calories we burn per whatever it is that we're studying, whether it's weight or speed. And this is really a very important little formula. It's exactly this, it's the two-dimensional analog of the formula that we did in the one variable case. There, we just add this. Now that we've got a second variable, we can do this. If we were doing 3 inputs, then we would add another. You know, you add as many as functions you've got. Okay, and so if we're at a certain point, and we know how it's changing in that direction, we know how it's changing in that direction, then we can estimate points near here, right? So this is going to be this number, 2,750, plus, well, in the x direction, we go up by 5, so we're going to add 5 times 4, we're going to add 20, because we've got more x, and we increase 1 in the y direction, so we're going to add 7. So we're going to add 27 more. So we estimate that this is going to be 27 greater than that. And of course, this actually gives good estimates as long as we are close to this value here that we're basing ourselves on. So this would be a good answer. But if I asked what is f of 200, 100, we'd be very nervous about our answer because we wouldn't really rely on it thinking it'd be that good. Okay, so just like we estimated the table by taking a short interval and putting it in the middle. We can do the same thing on a contour graph. Okay. So for example, if we're at 2, 1, we're at this point here, and we want to know what is the rate of change in this direction here, we just put down our ruler and we see that we go from 28 to 26. So straight away we see that it's negative. And it looks like we go down 2 in a run of 3. So it's minus 2/3. F12, we're at here. Now we're going in this direction. It's still negative, right? Because it's still going downhill. And now we would do this little guy here, because that's nice and short and it's in the middle. And it seems like it goes down 1 in a run of 1. So it looks like it's minus 1. So this is exactly the kind of stuff we did way back in when we first looked at derivatives. Okay, here is a partial derivative with respect to x positive or negative. Going in this direction, what's happening? Increasing, so therefore positive. Exactly. Here's another example. We're at P. What happens as x increases? Is it positive or negative? Positive. Positive, right? Because we're going from 3 towards the 5 contour. What about in the y direction? Is it negative or positive? Negative, right? Because we're going from the 3 towards the 1 direction. So this is sort of, so we can see this, it's kind of like a bank going down. In the x direction, we're sort of slightly going up. The y direction, we're going down. Here's exactly the same question that we did before, okay? So we know what a value of function is, we know what the partial derivative is. Okay, so we can estimate, so this is just an understanding question. It's just taking the information and turning it into formulas. So how much money do we get profit from selling 12,000 backpacks and 14,000 tents? Well, it's going to be F. F is our profit function, but X and Y's are in thousands. So X is backpacks. So this is 1214. Okay. What information are we given? We're given 1014. How do we get from 1014 to 1214? Well, we have to add 2 to the x direction. And in the x direction, the derivative is 4. In the y direction, well, the y doesn't change, so that's not going to affect our answer at all. And now we're ready to put the answers in. 1014 is 4. 2 times 4 is 8. What did I do? Oh, 23, sorry. 1014 is 23, isn't it? Right, 31. Okay. Okay, finally, the other kind of question you're going to be given is you're going to be given formulas. And to do any kind of problem with that, you're going to have to take derivatives, you're going to have to take partial derivatives. And so remember, the way you take partial derivatives is that you treat the other variable as a constant. So fxx means we take f, we take the derivative with respect to x, treating y constant, and then we take the derivative with respect to x again treating y as a constant. Whereas this, right, we take f, we take the derivative with respect to x, treating y constant, and then that answer, we treat the x as a constant and then take the derivative with respect to y. So this is a little bit confusing, these two guys, but luckily they're equal, so that removes a lot of the confusion. So we have second order derivatives. And so, for example, to figure out fxx, right, we have q, we say, well, if we go in this direction, we're going upwards. So fx is positive, but fxx is negative, right? Because the contours are spreading further apart. So it's kind of looking like this. So this, we know the first derivative is positive, the second derivative is negative. Going in this direction, right, again, the derivative with respect to y is positive, and we have to probably get maybe it's getting further apart. If they're getting further apart, then again it's negative. So finally, the thing I want to talk about is finding maxes and mins. So we take the partial derivative and we set them equal to 0. And then we've got this second derivative test where we take d, which is fxx times fyy minus fxy squared. Right? And so it's either, if d is positive, then it's either a min or a max, depending upon what the second derivatives are, the fxx's and fyy's are. It's negative, in which case it's a saddle point where it's 0, in which case it's indeterminate. Let's actually do an example. Okay, so let's have a look at these functions here. Which of these functions has a critical point at the origin? Well, we need to start taking some partial derivatives. Oh. Okay, what's the partial derivative of a with respect to x? Two x. Excellent. Okay. So the thing to remember is when we take the partial derivative with respect to x, y is a constant. So that's just plus a constant. It doesn't affect the change. What's the partial derivative with respect to y? Joe?
6y squared.
6y squared, exactly. B, derivative with respect to x, right? So the first term, we're going to get a 2xy, right? Because now the y is a multiplicative constant. Here we get 4x. And this is 0, right? Because it's adding a constant.
Would it be 4y?
Where?
Plus 4.
Yeah?
Yeah.
No, because y is a constant. If you add a constant, take the derivative, it doesn't affect it has zero derivative. Right? Because remember, if you've got x squared plus c, take the derivative of it, it's 2x. Adding a constant doesn't change the derivative, right? Because when you do rise over run, right, the c's vanish away. Whereas if you multiply by a constant, it stays, right? Because when you do that, the c stays, right? So you can pull out a c. So that's.
I meant the second term. It's a 4xy. I know that you make the.
Oh, sorry. You're right. Sorry. Oof, that's bad. Okay. Next one. Take the derivative with respect to y. We get x squared plus. Now it's 4x. And now we have a plus 4. C. Matt, what's the derivative of that with respect to x?
2x. Y.
Yep.
And then 4x. 4 minus 4x to 3.
Yep. And the y goes away. And then taking a derivative with respect to y, we get 3x squared y squared plus 2. And then finally, with cosine y. And then with respect to x, with respect to y, we get minus x sine. Okay, so which of these functions has a critical point at the origin? Does A, if I plug in x equals 0 and y equals 0, do I get zeros? So yeah. What about this guy? No, right? I get 0 here, but I get 4 here. So it's telling me in the y directions, it's increasing. And if I go in the negative y direction, it'll be decreasing. So it can't be a max or a min. What about this guy? No. Again, what about this guy? What's cosine of 0? It's 1. Right, so that's not there. Okay, so only A has a critical point at the origin. Function B has a local maximum at the origin, true or false? How can it have a local maximum if it's not a critical point? That's false straight away. Which of these functions does not have a critical point? Okay. Good question. Now this one does have a critical point, right? We've already seen that. Now, does this have a critical point? Can that ever be 0? Well, that's x plus 2 squared. When does x plus 2 squared equal 0? When x equals -2. So we have x equals -2. And if x equals -2, what do we get? Then we get -4y plus 4y. Oh, that's 0. Okay, so this one has a critical point. Can this ever be 0? So you've got a square plus 2. For this to equal 0, this would have to equal -2. Can a square ever be negative? Right. So this doesn't have a critical point. And this does have a critical point because cosine can be 0. And then if x equals 0, that can be 0 as well. So C does not have a critical point. Hang on, is this the same functions as before? Oh, no, it's a different. Oh, okay. Oh dear. But they're all the same ones. Okay. Instead of doing a whole bunch more, let's go back to this question here. Okay, so here we've got a contour map, and we want to know if there's a max or min. Okay, so we can see some that the highest contours is 6 and the lowest contours are -6. So this was like, again, so what does this landscape look like? So here, up here, we've got like a hill going up, we've got a hill going up here, and now we've got a slope going down, a slope going down. So it's a saddle point. So it kind of looks like. Kind of that sort of situation. So how many times does it occur? Yeah, because we've got yeah, because we've got a 6 here, here, and here. You can see it's 3 times. Yeah. Okay. Okay. So hopefully you'll get that's an idea of what to do. So that'll be the first half of the test. Or you could do it second if you want. Up to you. We'll meet together tomorrow and we'll talk about stuff from the first 6 chapters.